There will be one more homework assignment actually after the exam because there will be chapter 11. That's about the buckling, and that will be in the final. It won't be in. We haven't talked about it yet, so it won't be in exam 3. So exam 3 will be chapter 9, deflections. So you use equation, moment equation or load equation, determine the deflection, or use superposition. Whenever you can use superposition, always use superposition. It's easier, quicker, right? And then chapter 10, that is indeterminate beams. Again, whenever you can use superposition, use superposition. So that's indeterminate beam, chapter 10. And then we're going to have chapter 7, and that's the plane stress analysis, right? I think the main thing, major thing will be to be able to determine in which direction you're going to have principal stress, also principal strain, and also the maximum shear, right? Which direction? So that's the key parameters you should be able to determine. We'll focus more on the stress side than the strain side. Although we talk about for both plane stress and plane strain, you're going to have parallelly, you have more circle you can draw. Okay, but we will focus more on the stress side, and you can actually see from the homework, and there are more problems in the stress side than the strain side. The principle there is the same. All right. Okay, so today we're going to talk about a little bit more. That's actually in chapter 8, but we'll talk very briefly, just this one lecture. We're going to talk about the stress in pressure vessels, because that pressure vessel is actually very common. It's very common in engineering or other applications. So, for example, when you drive around, you see lots of containers look like this. Oh, sorry. Okay, here is on screen. Okay, so when you drive around, you see lots of containers look like this, right? A cylindrical shape, or sometimes can be a spherical shape, like a water tower. You can see at the top there is a spherical container, right? So for engineering practice, there are lots of times you need to figure out what kind of stress is in this kind of container, right? And so you can figure out whether it's strong enough or not. Because it's so common, so we actually are going to cover it a little bit today. All right. So first, we're going to talk about a cylindrical shape, a tube. Let's say you have a water pipe, or oil pipe, or gas pipe, right? What kind of stress will be in that pipe? So you can figure out what's the material to use, and if there are safety factors required, what the pressure there will be saved. So that's okay. So that's an engineering application. In the body, a very typical example is you have arteries and veins. So you want to quickly estimate what kind of stress in arteries and veins. Of course, even without the estimate, we know in human body everything is pretty safe, right? We have very high safety factor. So the artery or the veins, they can actually carry a much, much higher pressure than what we have in the body. But still, you want to figure out what's the stress. Because sometimes you have to do a substitute. When something breaks down in the body, right? We have prosthetic arteries or a knee, right? Or a heart or something. When you do artificial ones, you really need to know what's the stress there. Okay. Of course, real heart is actually complicated, but for a simple, estimation, we can always treat the heart either as a cylindrical shape, or spherical shape, or ellipsoid. So you can simplify, give some estimation. Okay. So we're going to mainly focus on first talk about like a pipe, like arteries or pipes or veins. All right. So when you have a tube. And oftentimes, in this case here, we talk about the wall is relatively thin. So thin wall tube. Because pipe, you see, most of the time, the wall it cannot be very big, right? The thickness cannot be very big. Because you want enough space inside to be passed enough fluid goes through it. So oftentimes we build the thin wall tubes. Okay. So how can we find the stress in a thin wall tube? That's basically the task today. All right. Okay. How can we find the stress in a thin wall tube in the wall, basically? Based on what we learned in previous chapter, how can you find the stress? It's supposed to be force over the area. Okay, that's a basic definition. Now, what's the force? Where can you find the force? Divide by what area? So the general idea will be you need to make a cut. You cut it open, right? Like get your free body diagram. So you can figure out the load and then find out the surface, the area where the load is applying. Okay, if you look at the tube, here is the cross section. Let's say we cut the cross section. Okay, so we have a load P applying here. That's all from inside. Of course, you can have a load pressure from outside as well. But what matters, you'll find it's actually the pressure difference. So what we have here, we call internal pressure, but actually it can be the pressure difference. Right? Imagine you have equal pressure from inside outside. Then, basically, since it will get even, so you don't have much pressure to the wall. The stress, the wall won't need to inflate or get compressed. So therefore, no stress there. Okay. So in a real world application, you are going to have much higher pressure inside than the atmosphere outside. So therefore, we talk about the pressure. That means the pressure inside -1. So basically, it's the pressure difference. Okay, so for this cylinder, how can we find out the stress? You find the force and the area. Okay, so let's say if I look at this block vessel here. Okay, if I draw this block here, I'm just copy this block, move to here. Now, what kind of load do you have on this block? You're going to have the pressure from inside, right? So that's all the pressure. What else? If I cut this small block from this wall here, what else are you going to have? The load on it. On the outside. Okay, what's on the outside? It's free, right? You consider 0 outside because we talk about the pressure difference. On the inside, you have pressure PI. So therefore, you have this PI, this load, times this small area applying there. Okay. Anything else on this block, if you look at? Shear. Where is the shear? I heard quite a few times shear. Where is the shear? Applying. Top bottom. Okay, on the top bottom, on this surface, you may have a force this way, and you may have a shear force this way. That's what you are saying, right? So in general, you should have shear force this way, and the tensional force this way. Okay, now, can we find out what's the tension force and what's the shear force? You have to make a cut, write the equation of equilibrium, and find it, right? That's the general way you can find it. Okay, so to find that, can we make it somehow a little bit easier instead of just look at this small block? Can I cut this cylinder into 2 halves? Okay, why do you want to cut it 2 halves instead of cutting that small block? If I cut the half, let's say if I cut it into half. Now, what kind of load on this half? If we draw the free body diagram, you're going to have this pressure here, right? That's what I already showed by the arrows. The pressure inside. What else? On this surface, you're going to have a force, we call it T. Actually, you can say force, right? If you say it's force, so I use F, because we talk about force, so it's supposed to be F, right? What else? You may have a shear. Let's say you have a shear, it will be V, right? We use V to label shear. Okay, if you have V on this side, what's the V on this side, on the left side? You should also have V, because imagine you look at this tube. It's axisymmetric. Everywhere is supposed to be the same, right? Can we agree on it's axisymmetric association? Okay, so if you have shear here, then you must have shear V here, right? Okay, now is this all the force possibly applying here? Right, that's all the force, because only here you make a cut. Okay, now let's say you have V this way. Now what about the bottom half? If you look at the bottom half, let's see, I just draw it here. Okay, let's say what about this bottom half? What are you going to have? Or maybe I'll draw it here. Make it looks a little bit better. If I draw it here, this bottom half, okay, on this bottom half, what do you have? You're going to have pressure, right? Then you're going to have this force, F, this way, because these two are action-reaction. They should be equal to each other. Okay, then you're going to have force this way, right? Also F. Now, what about the shear force? You should have point which way? Out. Okay, you should have out. Okay, now this one, out as well, right? A pair out. Now, what if you somehow stand upside down, or I rotate this thing upside down? What do you get? You get the same thing like the top half, but this shear will point outward. So, what can you conclude from there? The shear force must be 0, because otherwise, this part you're pushing outside, this side pushing inside. The two sides not symmetric anymore. If you want symmetric, you have to have V. So, okay, here we can conclude the V must be 0. So therefore, okay, only the tension F is there. Now, can we find out this tension F? Yes, we can use equation of equilibrium, right? Sigma Fy is supposed to be 0. Okay, now can we calculate sigma Fy? I have the equation here.
Is that distributed load?
Yes, that's a distributed load. Okay, and how is this distributed load? Now remember, this is not a straight beam. So the load here is always perpendicular to the surface, to the pressure. So it's always in the radial direction. So here the pressure is this way, and here the pressure is this way. Now, how can you calculate summation? You have to select, okay, this location, for example, I calculate here. This is theta direction. Here is the theta direction, right? So you're going to have a force here. Let's say call this one dF. Okay, so the dF should be peak pressure times this small ds. And that's the force dF. Okay, so let's write here. Let me see if I have the equation here. Okay, so let me write it here. So you're going to have this dF. Supposed to be the pressure times the ds. That's a small area, or dA. Let's call it dA. Okay, what's the dA? What's that dA? The arc length should be, that'll be what? R times this d theta. That's the small arc length, ds. Then times this dimension, right? The dense dimension. So that's a small URL. Okay. Is that correct? Okay, now this is a small dF. Now, when you try to write sigma Fy equals 0, how would the df contribute? You should project it, right? The component to the y direction, right? So you're going to have the df in the y direction, vertical direction, should be the df times cosine theta or sine theta. Where is theta? This is theta. So cosine theta or sine theta? Sine theta, right? Sine theta. Okay, so that's the contribution to the y direction from the force here, the df here. Now, can you calculate the whole thing? Yeah, just integrate, right? To theta from 0, 1 degree, 2 degree, 3, then until 180 degree. You should do that integrate. Okay, so here is the equation. Okay, so when you do the Fy, it's basically here. P, that's the pressure. R d theta, that's the arc length. Okay. And then times L. And then times sine theta. Okay, now where's the L? Why the L is not there? The reason is I'm looking at 1 unit length. Because the pipe can be infinity long, but it's all the same. So I can just look at the 1 unit length, right? So I'm looking at the L equals 1. 1 unit. I'm looking at that segment. Basically, it's a ring. I'm cutting 1 unit length of the ring, and then look at the equilibrium. That's why you don't see an L there. Okay, and that's why you call T. Don't call it F anymore. So T is basically per unit length. All right. So
that lowercase t in the equation, that's pressure?
no, the capital T. We're talking about the capital T. So the capital T in this graph is equal to F over the length L.
What is the small p?
The small p is the pressure. It's the PI. This PI is the P. So small p is the pressure. Okay, now when you, this is an easy integral, right? You know, something times sine theta d theta, an integral from 0 to pi, from 0 to 180 degree. So you can calculate it. So you can throw this constant out, then this is left here. So you have 2 pi. So very simple. The result is very simple, just 2 pi. Okay, now if you look at their x component, and it happens to be 0. Okay, why is 0? Because it's symmetrical. This side, they try to push this way. This side push this way, so they will balance out. That's why in the x direction is 0. All right? Okay, now what do we have? We basically have T equals PR. Okay, how do you get this one? Actually, I can jumping back one step before I show that. What's the sigma Fy equals 0? You're going to have 2T, right? Point downward, negative. Then plus the Fy equals 0. That's your equation of equilibrium. Right? For this half circle, for this half green circle. Right? I can write sigma Fy equals 0. So negative 2T and then plus the Py. Fy. Supposed to be 0. So that's, you have this equation. Okay. So from here, 2T, because this one, Fy, we already know it's 2PR. So therefore, 1T is 1PR. Okay. So we have that. Now, if we know T equals PR, now what's the stress? Sigma. Sigma is supposed to be T over the area. That's what's the area? This area, cross section. Supposed to be thickness times L. L equals 1, right? So therefore, sigma we'll find out equal to this one. You just divide by T because L is 1. Remember, L is equals 1. This is 1. So this is already for L equals 1. We talk about 1 unit length, right? Okay. Any questions? Or any part not clear? Lowercase t. Okay, what's lowercase t? It's the thickness of the wall. Actually, here, somehow I wrote down h here. It's actually lowercase t. Okay, so what's t? T is the wall thickness. All right. So the equation actually come out a pretty nice, simple format. The stress equal to the P times R over T. And how do you get it? You calculate the force of all this distributed pressure load, get their summation there. So that's a mathematical way. Okay, here is my second version, how you help you to remember or memorize it and give you a simple explanation. Why, okay, I'm trying to explain why the T should be equal to PR. Okay, here is my simple version. Okay, imagine you have this cylinder, right? Okay, so I have this cylinder here under pressure P. Now, what if I can equivalent this one to 2, have this one here? Let's say, imagine I put a membrane here. Okay, now if I have a membrane there, so I can divide this into 2 parts. Okay, one part will be this half. One part will be this half. They will be the same, right? Okay, so therefore, let me say if I have a pressure vessel like this, basically a half circle. Okay, this under pressure. Now, can I find out the stress in this arc part? I can do by making cut, right? So I can cut here, cut here. So I end up with one is at the top is a plate. At the bottom is this half circle. Is that correct? It's under pressure P, right? So pressure P is still here. Now, what's the tension here? What's the tension here? What's the tension here? What's the tension here? They're all equal, right? So they suppose equal to T, equals to T, right? This one equivalent to this. So tension will be T. Okay, so T will be applied on the plate, holding on the 2 sides. T will be on this circle, holding on the 2 sides. Okay, now can I quickly find out T? Yes, the quick way is, instead of calculate this one, you have to do this integral, because everyone changes the direction. You have to project sign and then do this, right? Now I can easily do on this one. So here's the pressure, right? Imagine you have this vessel, so inside is P. So on here, it will be also pressure T. Okay, now let me redraw this plate. So the plate I'll redraw it here. Okay, so on this plate, I have T tension here, T tension here to hold it. Why I need to hold it? Because the pressure P is applying here. Right? Now, this plate should be in equilibrium. Okay, now write sigma Fy equals 0. What do you get? What's this length of this plate? 2r. Okay, so this length will be 2r. All right, now write sigma Fy to it equals 0. What do you have? So you have this P times the area. What's the area? P times the area. 2r times the length. That's 1. Right? Suppose equal to the one that holding. Or you can say this way, minus the 2t equals 0. Is that correct? For this plate. Okay, now simplify this equation. What do you get? You get T equals PR. So that's a much easier way of thinking about it. When you forget about the equation, somehow you don't have a handbook ready, you can just draw that, calculate, oh, that's it, T equals PR. So that's a kind of a physical explanation. Instead of doing this mathematical integration, physically you can All right, so that's a simple explanation, T equals PR. Once you know T, right? So the stress is supposed to be T divided by thickness, right? Because that's our area, that dimension is already 1. So that equals to PR over T. That's it. So we find out the stress in a cylinder, okay, circumferential direction, and that tension there in the circumferential direction supposed to be PR over T. All right. And this will be applicable to all the thin wall tube. So like arteries, veins, we all use it. Water pipes, we all use it. You have a balloon, right? A balloon, tubular balloon. When you calculate, that's also applicable. You can use as well. Or the container we should show at the beginning, right? So when you go outside, you see the container, water tower, or whatever is used as a container. You can always use this to calculate the stress. Okay. And very interestingly, for example, when you look at the veins, for example, okay, the R, okay, always often like 10 times bigger than T. So it's a thin wall tube. Okay. So R is oftentimes more than 10 times bigger than T. So therefore, your stress is more than 10 times of the pressure. So if you look at the artery, you know the pressure, normal pressure is like 100 millimeter mercury, right? So the stress in the wall can be 1,000 millimeter mercury. So you can have very high stress. And that's the reason, actually, the arteries, the wall are thicker because the artery under pressure 100. And the vein on the other side, all the veins, the pressure, let's say, less than 10 millimeter mercury. So the veins you see often very thin wall because the pressure inside is much lower in the veins compared to the arteries. So therefore, the need for veins, you don't need the same wall, right? So over years of evolution, so basically our artery veins adapt to the need. So the artery build really thick wall, whereas the veins are very thin wall because the pressure inside is different. So you don't need that much material to build a vein. Okay, any questions about this tube stress?
This might imply that the wall is uniform, correct?
Yeah.
Or uniform thickness.
Yeah. So most of the time we talk about uniform wall thickness. Okay. But often we can use this one for non-uniform wall as well, because you can, as long as it's thin wall tube, so we can use this as an approximation. Okay. So if let's say you have a wall, as that's happening in a vein, for example, your wall thickness is not uniform. So you know that, okay, the thinner location will have high stress. So you know where the crack is going to start. Right. Okay, any other questions? Okay, so with all this explanation, the final result is actually very simple, just this one equation. Your stress will be equal to, we talk about circumferential stress, right, along the tube. So circumferential stress will be the PR over T. Okay, remember it's for thin wall situation. Okay, any questions? All right, if not, let's look at another situation. So more general, okay. So this equation, in general, we call it the Hooke's stress, or we call it the Laplace law. If you read the medical journals, they always talk about Laplace law, and that's the equation actually they talk about. All right, and in engineering, a lot of time we say Hooke's stress. What's Hooke's stress? Is the circumferential stress. That's a hoop, right? So Hooke's stress. Right. The same equation. So you can call it the Laplace law or Hooke's stress. All right. And the Laplace law actually can be general. That's for Laplace law for a tube is this format. If you look at an arbitrary membrane, 2D situation. So the Laplace law actually look like this. So you can have P over T equals sigma 1 R1 sigma T RT R2. Okay. So sigma 2 R2 sigma 1 R1. And so sigma 1 is the one direction. Sigma 2 is the other direction. So the two principal direction, you have two principal radius of curvature, and that's what you put here. Okay. This just kind of, we just mentioned this idea. We're not going to derive it or use it. Okay. Later on, when you study for advanced courses, you need to use that. Okay. But when you know what's the Laplace law, what's the Hooke stress, that's the concept. Okay, so the next structure we want to look at the sphere. Okay, spherical container. Okay, how can we find the stress in a spherical container? Okay, I draw it here. The pressure P is still inside. Okay, I draw this to look like a cylindrical cross section, right? Because sphere, if you cut in the middle, that's what it look like here. But make sure you know this is actually, we talk about spherical shape. Okay. So it's not a cylinder going this way anymore. It's actually, you can imagine you spin, that will be a spherical shape. Okay, again, if you cut a sphere, right? We can, for example, cut into two halves. Okay, here look like this. It's actually this one. It's a half two. I draw two lines. Actually, this line should be solid. You can see. So it's like a cap, you know, half sphere. Okay, now when you cut it, what's the tension there? What's the stress in the wall? That's the question we try to answer. How can you find out the stress in a thin spherical container under pressure P? Well, the one I just showed was for cylinder. So there should be some kind of small variation you can use it for spherical. How can we determine that? You can do the same way, right? Calculate, you cut it to half, then there will be T here. Tension T, right? And then remember now this bottom is actually a spherical shape here, a circle. So therefore, again, you have two ways of doing it. One is you calculate all the pressure generated force, and then project it to the y direction, right? Add all this together, integral, and then write the equation of equilibrium. Or you can use the other way. The second way I just explained. Imagine you have a sphere, right? Now you are equating this one to two half sphere. So you have a half sphere with a bottom with a plate. And you cut it off and then write the equation of equilibrium about the plate. You can get the force that way as well, right? Okay, so let me just quickly show the equation here. And then I'm going to use the next slide kind of explain how can you get this equation. All right, so imagine we use that physical approach. Okay, so we're going to cut a sphere into two halves. Okay, so for this half, you're going to have a bottom, you're going to have a disk here, right? And this closed container, half sphere, closed container. Pressure inside is P, right? To find out the stress, so I cut it, I make a cut. So I cut it one, the top will be the sphere itself, right? And the bottom will be just a disk, right? So spherical disk, that's the bottom. Okay, so for this spherical disk that I imagine I have in the middle, right? As a cap of this half circle, half sphere. Okay, this cap, on this cap, what kind of load do you have there? You should have pressure on all the area, right? Everywhere. Is that correct? Also, because it connects to the half sphere, so on the surface, I mean not on the edge, along this edge here. Okay, along the edge, all this, you're going to have the tension between the plate and the sphere, right? So you're going to have this. Remember, it's along this edge. Okay. So let's call this one. You can say, okay, I can say this will be stress. What I'm looking for, that's the stress. Right? If I know the stress sigma, let's call it sigma theta. I'm looking for this stress. Okay. I say the stress will be sigma theta. Okay. Because of the half sphere. Now, this load here is pressure P. Now, can I write the equation of equilibrium about this disk? Circular disk, right? Can we write the equation of equilibrium? Okay, so it should be sigma Fy equals 0, right? Okay, so therefore the F generated by the P, that's actually going to point upward. And then the force generated by this around the edge, the sigma. These two add together should be 0, right? Because on this plate, there are only two loads there. One is the pressure push around this disk area. It's like, imagine if you look at this bottom here, the water pressure is applying every location. Okay, now if I make a cut, then on this edge, the bottom edge here, right, you're going to have this sigma all the way along the edge. Okay, now how can you calculate this one? The force generated by the pressure should be P times the area. What's the area of this disk? Pi r squared. Okay, pi r squared. All right. Now, how can you calculate this one? Should be the stress times the area. What's the area? That's stress is sigma theta, right? Okay, what's the area of that edge? 2 pi r times the thickness. What's the thickness? We call it small t, right? Okay, this minus each other should be equal to 0. All right, once you have this, can you simplify it? This is sigma theta here, right? Okay, simplify. What do you get? You'll find out what you can simplify. You can throw away the pi, throw away a r. Okay, throw away r, throw away the pi, throw away r. Okay, what's left? You have PR equals to theta times 2t, right? Okay, now what do you get? Sigma theta equals to PR over 2t. That's it. So this way much easier than you do all the integral. Because now integral is all the sphere. Not 2D anymore, right? Spherical shape. Okay, so that's the equation. Oh. So this is the equation, right? Now let's go back, see if it's the same. Is this the same? Okay, it's the same, right? So now we have this stress for spherical shape. Okay, anyone notice how this equation is different from the one for the tube? Anything different? You have a 2 at the bottom there. So when you have a given diameter or given radius, okay, this cylinder, if you build a cylinder, the stress is going to be twice higher as you build a sphere. Right? So or in other words, sphere gives you the best structure. It's minimize the stress. All right. Okay, any questions? So we end up 2 equations, right? the stress for a cylindrical tube and the stress for spherical container shape vessel, right? And the stress very similar, except that they differ by a factor of 2. Okay, that's the 2 equations basically. All right. Okay, next, let's look at the one special situation. That is when you have a cylinder that's very limited time, limited length. Okay, as what you see around, outside when you drive around, you see lots of container, right? Either stick there or flat or vertical. Okay, so when you give a cylinder with a limited length, what kind of stress do you have in this cylinder? Right? The pressure, there is a pressure P inside. Okay, can you find out what's the circumferential stress? We just talked about it, right? So you can make the cut as shown here. You're going to have this equation. So we already showed that. Now, for a container, like a Coke can, imagine we have a can of Coke. There's pressure built inside. So circumferentially, you're going to have this much stress. Now, is there any stress in the longitudinal direction? Yes, because the pressure there is also trying to push the two ends, try to push it apart. Right? Imagine you have a very soft rubber tube there. You pump air there, you're going to elongate. And that's actually the balloon, the stuffing balloon, right? We actually see that when you pump the balloon, it gets bigger, also gets longer. And that's the reason. So there is another stress in the longitudinal direction. Okay, how can we find out the stress in the longitudinal direction? Same way, you cut at the end, right? Look at the end plate. You cut it there, that's how much stress you get there. Okay. And then this stress, this force here, if you calculate the summation of the force, should equal to the pressure generated force to the end plate. And that's basically P times the pi r squared. Right? These two should be equal. So with that, you're going to have this equation in the longitudinal direction. And that gives you this equation. And it happens to be the same equation as a circle. As a spherical shape. So we still end up with 2 equations, no more. Okay. So when you look at a Coke can, okay, circumferential stress will be PR over T, but the longitudinal stress will be PR over 2T. So the stress in the longitudinal direction always half of the circumferential stress. So if a Coke can break, it should break around circumferential direction, not along the longitudinal direction. Yes?
Does that matter because of the shape of the Coke can? Like, the Coke can's got a dome bottom, so therefore it's not the same.
Well, that's slightly different because that's a detail shape there. It causes some stress difference there. So we talk about perfect ideal situation. You have a nice cylinder, a perfect flat end there. Yeah. And also, remember, we talk about small deformation. We ignore the edge effect, ignore the stress concentration. In fact, if you look at the Coke can, let's say, let me draw one here. Okay. In fact, if you look at this edge here, it's actually not that simple because there will be this side, they try to push this way, this side push this way. So there will be a bending effect. But we ignore that small local effect. For accurate analysis, you actually have to include that effect. We're not talking about ideal situation, so there's no this end effect considered there. All right? Yeah.
So the stress really is when you're calculating it in the longitudinal direction. I mean, it could really be any shape. It just comes down to that contact point, that circular contact point.
Yes.
It could be anything.
Yeah. So when you have a container, the end doesn't matter what's the shape, because far away from the end, you're going to have this equivalent. It will be like a pressure compressed on a surface. This is pi r squared, and not pulling this tube longitudinally. Yeah. So the shape there doesn't matter anymore. the shape only affects this local stress. To this middle part, it doesn't matter anymore. Right. All right, so in general, if you draw an element on this surface of a container, you're going to have this piece, right, a metal piece or a rubber piece. You're going to have tension around circumferential direction and tension around longitudinal direction. All right. So here's another question. Can you draw the Mohr circle for this point? Remember, we tried to draw a Mohr circle. Okay. Can you find the maximum shear in the cylinder? All right. So I'll leave this for you to think about. We'll continue to talk about this next time. All right.
In your office, where you might have about 5 minutes to show me something.
Sure.
Great, thank you. Shouldn't take long.
Thank you.
I've got most of it wrapped up.